Well, welcome back to our discussion of rocks. We're going to cover metamorphic rocks and in particular focus on the formation and the environments in which these rocks are formed. The conditions that we need to form metamorphic rocks are conditions of elevated pressure and temperature. Okay. Typically, the easiest way to make a lot of metamorphic rocks is to stuff them down into the Earth's interior, or to bring something hotter from the Earth's interior, okay, up closer to the surface. So if we want to get a rock from the surface and metamorphose it, we're going to send it down, okay, which will change or by increasing its pressure and temperature. Or if we have a rock up here and we want to get it hot and metamorphose it, maybe we'll bring up a magma or hot rocks up here, which would heat things up and change pressure and temperature as well. Okay. A lot of rocks we'll see are formed with stress or involve stress, and that stress forms a kind of structure in the rock called a foliation. There are different kinds of stress in the crust. Compressive stress that you're seeing right here on the top right corner, where we compact perpendicular to a horizontal plane. We also have shear stress, which we see on the right hand side. In this case, the compaction or the flattening, the movement is parallel to a particular plane rather than perpendicular to the plane as shown in the top diagram. But the net result is the same, that you end up with an alignment of minerals. So on the rock here on the far left, no alignment, homogeneous more or less. Now we have on the right hand side, the rock is subjected to stress. It creates an alignment. This alignment forms in the solid state. It means that minerals, for instance, the black mineral, the white mineral in here, they will dissolve and regrow in an alignment in accordance with the stress that's being applied to them. Right? On the bottom right, we see a set of rocks that are not stressed. Apply stress to them, and you get the rock at the top here. Okay? And you can see, here's a scale, centimeters down here on the bottom. These used to be part of a sedimentary rock, interestingly enough, called a conglomerate, which we showed you in the previous segments. And they've gone ahead and been flattened by compressive stress, or mostly looks like compressive stress. They haven't been terribly sheared. I was looking to see if I see a lot of shearing. No, there's some shear bands in here, so there could be some shearing going on. Excuse me. Something like that. The result is a kind of foliation, and you can see it in the rock texture. Yeah, sure enough, as you might have guessed, sedimentary rocks, igneous rocks, classified based on their texture, whether they're made of grains that were collected, whether they're made of grains made by organisms, whether they're made of grains that precipitated in an inorganic environment. So we're interested in rocks that are foliated, okay, or non-foliated. Back up for a second. This alignment of minerals or alignment of old clasts that have been flattened is the foliation. Okay? So in the rock on the bottom left, we're looking at a rock under a microscope. We see all of these green minerals here and all these sort of black spots and white spots here. Do you see any alignment of minerals whatsoever? Nope. However, it's very easy to see on the right-hand side, and here, there's an alignment of the mineral muscovite and biotite running through the rock like that. So this rock on the left is non-foliated, okay, and the rock on the right is foliated. So texture becomes important. This foliation, or the absence of it, becomes important. And of course, the minerals that are present are also used to classify the rock. Metamorphic rocks show up at different temperature conditions and have different behaviors. The minerals grow to different sizes. So we often start at the lowest grade here at about 250 degrees. That's about 250 degrees Celsius, and it'll be increased temperature. And to some degree pressure is involved, but mainly temperature. We go from low-grade foliated rock like slate to phyllite to schist to gneiss. And then what happens to the rock after gneiss? The gneissic rocks are still solid, but if you cook it even a little bit further, okay, you get migmatite. And a migmatite is a melted rock. Okay? Migmatite is not metamorphic. It's not igneous. It's a mixture of melted rock and metamorphic minerals. So it's what we call a mixed rock. It's neither one nor the other. So just blow up this diagram a little bit, or from the previous diagram, blow it up. And we start out with low temperatures here, increase, 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 and we're at high. Okay. This is gneiss. I'll write that right on there. G-N-E-I-S-S. This is a schist. It's a foliated rock. This is a phyllite. This is a slate. Okay. If we take a look at the crust, the crustal structure in, let's say, Illinois or someplace that's not tectonically active, would we find metamorphic rocks below our feet? And the answer is, of course, because the Earth's temperature increases with depth. Okay, so that means that the grain size and the foliation will increase with depth as well. We call that metamorphic grade. So let's just think about the rock names I listed: slate, phyllite, schist. Here's another kind of schist, and gneiss, and then finally migmatite. Slate is low grade, it is low temperature, and so it's forming closer to the surface. Okay? Phyllite is a little higher temperature, it's a little deeper. Schist is a little higher grade or higher temperature, it's a little deeper. Down to gneiss, which is the highest grade or highest temperature, and is the deepest. And then finally, below that, we run into migmatite. Now, how do we get rocks into the earth? Right? I told you get one of two things. Put hot rocks next to cold rocks, or put rocks from the Earth's surface down into the Earth's interior. And one way to do that is through this process of subduction zones. This is, we call it convergent plate boundary. So we have one plate moving in from the left and the other plate moving in from the right. This segment of the crust here, or we call the lithosphere. I'm going to write that word here. The lithosphere is being pushed down into the Earth's interior at this convergent boundary, and the other plate that's also got the lithosphere here is staying up high at the Earth's surface. And so one way to get rocks to go down into the Earth's interior is at plate boundaries, okay, where they get subducted. The other idea is that we can take a magma and we can bring a magma up into cold rocks, and we can bring magmas up into cold rocks and then cook the rocks around them. These have been cooked or metamorphosed. Okay. This is called contact metamorphism, right? Hot rock in the center, this magma is in contact with the surrounding rock. So all this area around here would have been cooked or metamorphosed. If we ask the question, well, how much area is affected by this? This is relatively small. It might be somewhere between 10 to maybe 50 kilometers squared, right? So it could be bigger than that, but 10 to 50 kilometers squared is pretty big. If we back up again, what's the scale of this? Well, this is the scale of the entire edge of a continent, right? So that means from, Mexico all the way up to San Francisco, past up into British Columbia. All of those areas have been experiencing this kind of subduction, and in some cases it's still active. So all of them would contain these kinds of rocks, and that means that we're talking about hundreds and thousands of, thousands of square kilometers of being affected by dynamic or dynamothermal metamorphism, or your textbook will use a term commonly called regional. Okay, regional just means large area. Okay? Contact metamorphism is relatively small. In fact, this picture of my intrusive rock intruding into the country rock actually fits in this dynamothermal diagram right down in here, right? There'd be a pluton that's relatively small in there, cooking the rocks around it. So they're not unrelated or unconnected. Okay? So, changes in pressure, changes in temperature create metamorphic rocks. Of those rocks, we're interested in texture and we are composition, but we didn't talk about that too much. And a foliation is when you've got an alignment of minerals in a rock. The other side of that is no foliation. And these places, the places where metamorphic rocks are occurring, require magma, so some heat source to be brought up or some rocks to be pushed down into the Earth's interior. And that does it, just about does it for metamorphic